I think we can start. Welcome back, everyone. And congratulations again on getting through midterms and getting through the second exam in this course. This is kind of a good place to be. As far as exam two goes, I'm not too far in grading them, but Mondays and Wednesdays are my busy day anyway. I should be in better position to get these graded up probably on Thursday morning. So I'm on pretty good target for getting these returned next class. Well, that's our major comment. And aside from the exam, one thing that has been brought to my attention, I actually noticed earlier, just in the grade book when I was updating grades, which I do pretty much on the weekend and before class starts, is that a couple people in the class have opted out of the book bundle, which probably made a lot of sense. But that means if you go to MyStats Lab, instead of actually seeing a button that says launch the MyStats Lab, I think that's what it's called, you'll just see something that says buy now, which is really, really confusing. And I was showed by a student in class, when you click on that, it just takes you to the bookstore with like a dead end. You have to actually find the right material, and there's no real indication if you're finding the right thing or not. That's extremely concerning. So if you're one of the people that opt out of there, I'd say hold on for just a moment, and I'm going to contact the course coordinator. I should stop right there. By course coordinator, I'm not sure if I mentioned this before, but that's one person that works in the math department that is in charge of every single math 1153 class, whether it's 1153P or not. And that person is the one who decided to use the book that we're using and the MyStats lab that we're having this issue right here on. So I'm going to contact that person, figure out what the right course of actions are, and get back to the class immediately on that as soon as I get an answer. So I'd say the best thing to do at the moment is don't spend any money, since the worst thing to do is to buy the wrong thing, get in a lengthy refund process, and still have to buy something else to make sure you have the right product. Well, any questions, folks, about this problem right here with the MyStats Lab and the book bundle? Okay, so it doesn't affect everyone, but the people it does affect, that's very, very serious. And it really sucks because if you opted out, it's because it made really good sense. You're saving money. So you shouldn't have to deal with this extra hassle. Sorry about that, but we'll get this figured out and hopefully it won't be as bad next semester. So where we're at so far is example 5 on chapter 2. We're probably about halfway through these notes is what I'd say. Probably in a position to finish them today or maybe early next class. Then next class is probably the most exciting place to be in this entire course, because we're finally doing what we refer to as inferential statistics. Essentially, everything we've been doing from chapter 1 all the way through to chapter 12 was to get us into a position where we could do these kinds of things. So section 13.1 is pretty abstract, but before very long in chapter 13, we're going to be doing this. Going back up to this problem right here, and actually describing that error. What we're going to do is come up with something called a confidence interval. We like things with 95% confidence, 99% confidence. And we'll just say that the unknown parameter P is within those two different values that we come up with. Really, this is just applied probability. And so that's why we've been doing lots of things in probability all the way up to this point. Just to run through the things as a reminder, our work in probability actually started in chapter 3 when we were looking at two-way tables and we were asking what percent of individuals fit some criteria. We could have just said, what is the probability a randomly selected individual fits that criteria? And we're doing the same exact thing. Then in section 5.4, we're working on the normal distribution. All the questions asked things along the lines of what percentage of individuals have, say, maybe a blood arsenic concentration above a certain amount. But the whole question could have been just, what is the probability that a randomly selected person meets that criteria? So these are really probability sections that we're doing in earnest. And chapter 12 is just trying to make that a little bit more formal. Chapter 12, like I mentioned, is pretty abstract on its own. We're not going to ask a lot of major questions on this chapter on a real exam, whether it's the second exam or the final exam. Think of chapter 12's major purpose is to bridge the gap with the first part of the course, descriptive statistics and probability topics, with what we're about to be doing next, inferential statistics. So that's my spiel to start the day out. Any questions at all, folks, with where we're at so far? Okay, well, let's take a look at what we've been doing so far in probability. we left off on this part right here, and that's kind of a lot of stuff. So let's back up and just see what we did recently. So calculating probabilities, if it's on a real exam question, I'm going to indicate this on the notes on every problem where I feel like this is a typical problem you would really see on the actual exam. And all we did in this problem was, if we want to calculate a probability, say root size is 5, we use the fact that we're randomly selecting one of the 5,000 nests or one of the 5,000 observations or outcomes in the sample space. So we divide by the 5,000 possible ways. And if the root size was at 5, we just selected 1,760 ways of getting those next. Again, that's almost exactly what you were doing on exam 2 on the very first question, except it was a two-way table, and this is a one-way table. That's the only difference. Well, any questions, folks, with any of the computations on that example 4? Okay, going forward on these notes, here's where we can collect a couple more ideas. Axioms of probability, again, is something that seems kind of wild because of how long this is. But these are things that we've seen before. We're just saying them once and for all in one spot and calling them the axioms. What we mean about axioms are, these are the things that must hold true for any system where we call it probability. So we have to have a sample space. A can be any event. So it could be just a single outcome, multiple outcomes. If we want to say the probability of A occurring, we just write this out. And next, here's the next new thing. If you want to say A does not occur, we use this symbol here, A with a superscript C. The way this is read as is AC. If you're just reading that out, it means A complement. Not complement as A is nice, but complement as a piece that makes up a whole. So a complement denotes the event that A does not occur. So if you write probability A complement this way, we're asking what is the probability A cannot occur? So there's A complement, and right away it's tied in with this thing, the complement rule. It says the probability of A complement is always 1 minus the probability of A. And it's in that sense that A and A complement make up the whole. The whole is the 1 right here with total probability of 1. So we're pretty much right here in the notes, looking through the definitions. And the complement rule right here, that's kind of amazing in a certain sense. We've actually used that thing, probably more than once, but the one example where that came up really strongly in my mind, where we're using nothing but the complement rule, was this problem here. Let's take a look, just to connect the dots. It was actually in section, I believe, 5.4, maybe 5.3. Let me open that one up just in case. And in 5.4, let's see here, we did a problem with corks. I don't know if you remember that one. It's been a while. Here it is, a machine that cuts corks. I think this is the right section. Let me close that one. So we had a pretty tricky problem on part A. We want to find the probability. Well, this one is not too tricky. I take that back. We just wanted to find the probability that the cork's diameters are between 2.9 and 3.1 centimeters. So this was our diagram. Or hang on, let me read this again. The specifications of the wine bottle call for corks with diameters between 2.9 and 3.1 centimeters. And we want to know what percentage of corks produced by this machine have the required diameter. Yes, between 2.9 and 3.1. I think the yellow highlighting just kind of threw me off there. So we found the probability of this shaded region, not the yellow shaded region. And we said the probability was 0.2689 altogether. Then part B is suddenly a lot harder of a question. Let's move this down just a little bit. Part B wants to know, what is the probability a cork produced by this, let me say this again, a cork produced by this machine, sorry, talking's hard today, has a diameter smaller than 2.9, so we're in this region, or larger than 3.1, so in this region. That could use normal CDF twice, and then you'd have to add your answers together. It's now suddenly really tricky to do this one. But the way we actually did it was this way. We knew the probability of A, so to get the complement, that's this piece, the side on the outside, we just took 1. Sure, it's a percent, but it's still just 1 for 100%. That's the 1 right here in this problem. We subtracted a probability we already knew. That's moving and subtracting probability A here in the complement rule. And again, this is what makes a complement. We had 1 piece here. This is the other piece. And if we put them together, we make up the whole for probability 1 altogether. So that's the essence of the complement rule. We'll use these in these notes, but sometimes the complement rule is a fast way to compute, like here. Other times it's almost just a required way to compute, depending on the given information of the problem. So I guess we wanted to look at property 3 just because that definition came up for a complement. Let's actually put this in bold just to make it look like a new definition, something to pay attention to. Property number 1 is something we specified at the top of the notes. We said, doesn't matter what the event A is, the probability of that event is always between 0 and 1. Think of 0 as 0% chance it occurs, 1 as saying there's a 100% chance this event occurs. So we're just saying what the likelihood could be. If you take the probability of the entire sample space, you're allowed to, but that's just probability 1. And finally, this is our good old complement rule. We'll use it here in these notes. That finally takes us to the new property 4. But first, any questions or comments at all, folks, with properties 1 through 3? Okay, property 4 is interesting because it has a name. This one's called the addition rule, but it also has a property of disjointness. We say A and B are disjoint events whenever they have no outcomes in common, which would mean they can never occur simultaneously. Either one occurs, which excludes the other, or the other occurs and the first event couldn't have happened then. So that's what happens with disjoint events. Let's say it here. Events A and B are disjoint when they have no events in common, or you could just say AB are disjoint whenever they cannot occur together. For example, maybe A is the event that Mike Jacobson is in Idaho Falls at 5:42. B is the event that Mike Jacobson is in Pocatello at 5:42. Those are disjoint events. Only one can happen. I don't want to be split in half to be in both places. And so those would be disjoint events automatically. What's nice about disjoint events is we have a new rule called the addition rule. If you take the probability of A or B, then it turns into an addition. You just add up the probabilities of the event A plus the probability of the event B. So that's the essence of the addition rule there. Another way to think about this is whenever you're dealing with the addition rule, an or comes up in the wording of the problem, and then it converts over to plus when you go to add up the probabilities. So think of an or as a plus. And while we have that thought, here's another thing that goes on in these notes. Or goes to a plus with probabilities, but there's another type of logical operator. Instead of saying or, you might say and. We've dealt with ands before. And gets tied together with times or multiplication. So this one is for the addition rule. Whenever an or occurs, and if an and occurs, that one is going to be some kind of multiplication rule. So that's our axioms of probability so far. Really, the best way to get to know these things is just to work with them. But think again, think of these as in these terms. Properties 1 and 2 are just carryover from the notes. It's really just property 3 and property 4, which are the new things in this right up here for axioms. So let's scroll down to this point, since that's where the new stuff is. So this takes us to our next problem, example 5. And let's add again to the notes that this would be a typical exam 3 or final exam problem. I'm not sure if I said it the same way on the other one that we indicated, but on the other one, it's a typical exam 3 problem or a final exam problem as well. So here's the setup on example 5. Nothing too major. It just says, at a particular college, a bookstore sells books in several formats. That makes sense. They have hardcover, paperback, digital. That's what we're suffering with some ISU book bundle issues, and audiobooks as well. So that's pretty routine, I'd say. It goes on to say, the manager of the bookstore, based on past sales, gives the estimated probability of that a randomly selected purchase will be one of the formats. And the bookstore manager really needs to do this kind of stuff, since working at a university bookstore is kind of a crazy hustle. Their markups are huge. So a lot of people don't even use the bookstore, yet they need to market their bookstore as being important somehow. So they have a lot of really technical work to do. They're going to be looking into their data to try to optimize and somehow bring in more money, because it's usually a losing battle for them. So this is what the manager came up with. We have probabilities of 0.16 for hardcover, 0.36 for paperback, and so on for the other formats. But the moment we see all this, here's another neat thought we should think about. Every one of these things are a type of event. The sample space is the hardcover, paperback, digital, and audio, so we ought to give a name for each one of these. The reason for that is, if you look at all these formulas here, they involve the events and a probability set function. So the more we kind of work with this language, the easier the formulas are actually to use. If we never write down probability or an event, we might be doing okay on some of the probability questions, but other ones that are much more heavily formula oriented become mysterious out of nowhere. So let's take the extra time on this problem and just give letters for the events. If this one's hardcover, we can call it the event H, much like we said H for heads in a different situation. For paperback, you could use the event P, but I would say that's discouraged because we already use P for probability. So if we can't use P, we could just go off to the next letter, Q. Or some other symbol would be just fine. After that, it's digital. So D for digital seems to make sense. A for audio seems just fine. Only one that seems a little bit crazy is Q for paperback, but that's just to avoid a conflict of notation. So we've got our events down. Below is the probability of each one of those events. And now here's how the problem starts. It says, if a purchase from past sales is selected at random, what is the probability that this purchase is for a book that is, starting off, digital or audio? Well, this one's not a hard problem. You would just take the digital probability, the audio probability, and add them together. But notice once you've done that, you've made really a pretty huge assumption. Also, if we're using the probability set function, we'd probably start off by writing it this way. Probability, D for digital, I'll just literally write down the symbol or, and then A for audio. If you're writing it down this way, the question we have to ask ourselves now is it possible for a book to be both digital and audio? Absolutely, right? But looking at how they wrote this out in the bookstore, it seems like the manager's saying those are exclusively digital titles, and those are exclusively audio titles. So if we make that assumption, we're saying that D and A are disjoint. So let's say that here, assuming D, comma A are disjoint, this equality here turns into probability of the digital book plus the probability of an audio book. But again, that is a really, really huge assumption. We're assuming, once again, just to reiterate, that when the manager put out to this table, that there was no overlap. All the digital titles are here, all the audio titles are here. And if that's really the case, we're saying that they are disjoint events. There's nothing in common. There's not a lot of information to say definitely they're disjoint or definitely they're not disjoint. It wasn't really written up into this problem. So sometimes when we calculate probabilities, we're making our own assumptions right at the get-go. So assuming disjointness, which may or may not be the case, we're going to say that this is equal to Probability of D, 0.40, plus probability of A. Here we're just making substitutions and plugging in 0.08. So this gives us a probability of 0.48.
Can you clarify when making that decision of disjoining them in a quiz or exam, or would you make the same assumption?
I would make the same assumption, yeah. If you did put this clarifying statement in, that would be okay. I mainly like this kind of problem because it's easy to miss that we made that assumption. But think of anything written in orange as stuff that's just extra to the notes, not required for the full solution. Other questions at the moment? Okay, so like people said in class, it does seem plausible that if we didn't have extra information whatsoever, maybe these are not disjoint. I would question what the bookstore manager is doing then, if that's the case. Probably this is not the greatest data table for us. But if those weren't really disjoint, then we don't have the right answer. And in fact, it's even worse. We can't answer the question at all if those were not disjoint events. We would need more information. We would want to know what's the probability that the book is both digital and audio all at the same time. So making that big assumption right there, we could at least calculate something. We're saying that there's a 48% chance the book is digital or audio. Any questions, folks, so far? Okay, so essentially from here to here, this is the so-called addition rule for disjoint events. So next one says not a hardcover. It's not asking for probability of H. So as written, this is wrong. If we add something here, we can make it correct. We only just looked at this, so if you've forgotten, no worries. But anyone recall what should go here? What extra symbol we have to attach to H, essentially? Sorry, say again? No worries. It is, absolutely. When it said not to hardcover, we're taking a look at the probability of H complement, the probability that H does not occur. So I'll try to be very careful with the highlighting in yellow because sometimes these elements in the writing are easy to miss when you go to write the probability statement. And notice there's also two ways to do this, certainly. If you're asking what's the probability of not a hardcover, some people might go this way. Well, here's hardcover. They're referring to all the other stuff. So just take 0.36 plus 0.40 plus 0.08. And that's the right probability. It certainly works. You wouldn't lose any credit if you did it that way. But I'm going to do it a different way because we have a brand new formula right here, the complement rule. So just to show how it goes for problems where it's really required, we'll try it in this simpler situation. It's kind of neat that we can do it in the simpler situation because now we can just check our intuition on what the complement rule is even trying to say in the first place. Let's just park it right there for the moment. We also need that table up here. So the probability that your book is not a hardcover by the complement rule is 1 minus the probability that the book is a hardcover. This is actually faster to calculate in the first place, so it has that added benefit. If our table was much bigger, it'd be spectacularly a lot easier to calculate. We just go 1 minus. Look up the probability of H, it's at 0.16. And certainly 1 minus 0.16 is 0.84, matching up with the values that we have in the calculator. The reason that works is the only way I can actually give you a table like this and have it be a probability model is if all of the earlier axioms of probability hold. Every one of those probabilities have to be between 0 and 1, and the probability of the sample space, that's adding everything up exactly, has to also be exactly 1. We never verified that. There's, I guess, a lot of trust in this, so let's see if that's really true. We added up these three right here. We got 0.84 plus not that, plus 0.16 gives us probability 1. So that's what's being conveyed right here on our second axiom of probability. Probability of your entire sample space must always return 1. And all this was right here, again, just to reiterate, is the complement rule. Well, any questions, folks, with part B? Okay, next one is, I think, kind of tricky because it says a printed book, and then we have to find the right outcomes. Let's leave this one up to the class. What would you say goes inside here based off the wording in part C? Exactly, we're gonna go H. I like that you said plus. Inside the probability function, it'd be an or, but plus is just a reminder that we're using the addition rule now. And so we'd go probability of H plus probability of Q. Once we write that down, we come up here, look up the values, 0.16 plus 0.36. And I'm not sure if I trust myself to that mental math, but I'll give it a try. Looks like a 0.52 in probability. Yeah, that feels right. Does that look all right to folks so far? Okay, so getting through example 5, you might say, well, did we need any of this really? Probably not, right? You could just grab the values and add them together and get the right answers here. So think of example 5 as its major purpose is really just to think about those axioms of probability, what they're trying to say, and how to use them. It's admittedly not the craziest example, and we put in a lot of writing to get to answers. You might have just eyeballed it and jammed them into the calculator, which is okay as well. So after getting beyond example 5, I think this is where the content starts to get a little bit more difficult and tedious. So some of these problems that we're doing is, just for the sake of helping out in the homework, getting a little bit more intuition and probability, we're getting down to the problems where I probably wouldn't ask these on real exams. So think of these questions here as more, we're just filling out our understanding of probability before we jump into chapter 13. We have the good old addition rule. In fact, we used it right here in part C. Let's just say it here as our reminder. The or turned into a plus. We added probabilities of events. So this is the addition rule for disjoint events. But events aren't always disjoint. Here, no one did have any qualms about this one because if you say hardcover or paperback, that's what Q was, let me just double check, that absolutely sounds disjoint. More so than digital or audio, that seems like there could be actual overlap inside there. But when things are notably disjoint, all you're doing is adding up the probabilities. So what happens when they're not disjoint? Well, we still have a rule, but it's now called the general addition rule. You start by adding up your two probabilities. That's like what we did here, probability of H plus the probability of Q. But then in the general addition rule, you do this subtraction right here. Let's highlight this part in yellow. So let's imagine what this is really doing. If A and B are not disjoint, they have overlap. There's some bits of B inside A. Inside B, there's some bits of A. So if you go to add probability of A and probability of B together, you have double counted the thing that's in common. And the only way to counteract that is this. We subtract once the thing that's in common, probability of A and B. That's the idea of the general addition rule, but it's honestly really hard to visualize why the rule changed so much, what this is really trying to say, unless you put in a really good picture. That good picture is going to be called a Venn diagram. So we'll use the Venn diagram to help us out through example 6. But first, let's take a look at how it started. Actually, let me just bring that back to where it was. Example 6 says, congenital sensory, let me spend some time with that. Sensorineural deafness is the most common form of deafness in dogs, and it's often associated with congenital pigmentation deficiencies. So if your dog is deaf, they might have some issues with their eyes as well, their pigmentation. I like this problem because I had a Dalmatian as a child, and they are interesting dogs. Fun fact, I think the reason they used to use Dalmatians, I don't know if they still do, for fire issues is these dogs are kind of nuts, and it might have had something to do with deafness as well. there's just a lot less fear when you can't hear anything crashing and burning around you. So a real study found 28% of Dalmatians were hearing impaired. That is a lot of them. So if you have a Dalmatian, maybe that's why they're not listening to you. You have to use other methods. 11% were blue-eyed. That's kind of interesting on its own. And 5% were hearing impaired and blue-eyed together. So we have two events, but three different probabilities we have to take care of. Best way to deal with all this is just to start organizing. So first event is hearing impairment. Let's let that be the event H. We have a probability for H. We can just paraphrase over here on the margin and say probability of H, your Dalmatian is hearing impaired, is 0.28. So 11% of Dalmatians are blue-eyed. That's got to be color-coded blue, or else this problem will make no sense whatsoever. So I'll point to blue-eyed to say that's the event B. Down below, we can say probability of B is 0.11. The next probability is tricky though. It says, and 5% were hearing impaired and blue-eyed. Turns out that word right there is extremely subtle in probability. Whenever or an and comes up, that and is more important than it looks like, because when we take this probability highlighted in yellow, we're writing this out. Probability of, let me fix my colors real quick, H and, oh, hang on, let me fix my H. My H is supposed to be green. B, there we go. So this probability, I forgot to include it in the yellow highlighting. There, we've got it now. This probability is extremely tricky because it's referring to an event where two things happen together. The Dalmatian is partially or fully deaf and blue-eyed all at the same time. So we take that probability of 0.05 and label it this way, 0.05. So notice that's actually pretty critical if you're going to use the general addition rule exactly in this format. We had to know what is the probability of the overlap, because these are not disjoint. Dalmatians can be hearing impaired, they can be blue-eyed, and there's a 5% chance they happen together. Well, any questions so far, folks, to this stage? Okay, so it takes a lot of work to kind of digest this stuff, break it down, and everything we're doing here, labeling HB and writing out all these three probabilities, is just taking the problem and writing it in our language, so that when we go to use this formula, oh, did that weird, this formula, we know what goes where and why. So let's get back to the main question. It says, let's call this method 1. We don't often do this, but this is a good problem to try it and see from two points of view. In method 1, we're just going to use a general addition rule and see how it goes. What is the probability? So from there, we can write probability of something that a randomly selected Dalmatian is hearing impaired or blue-eyed. Now, the critical word in this write-up is the word or. Missing the word or can lead us on a wild goose chase to get the right probability. But if you spotted it, that's great, because it reminds you now you're probably using the general addition rule. You need an or there, which conveys to a plus. So probability hearing impaired is H, or B, blue-eyed. So we want that probability. And it's always good to compare what we did prior. In the prior problem, we did one just like that, H or Q. This was hardcover or paperback. But because there was no overlap, we just added up the events, probability of H plus probability of Q. Doesn't work here because there is overlap this time. So we go probability of H to start plus probability of B next. Just put a quick border there, then minus probability of H and B. So that's our probability to calculate. The nice thing about the general addition rule formula is that once you recognize how it goes together, you're just dropping in numbers. So here's how they substitute in. For probability of H, we're throwing in the 0.28. Probability of B, we're throwing in the 0.11. Then we're subtracting the thing in common, the overlap, which is 0.05. So that's a fast computation. Back in the calculator, it's 0.28 plus 0.11 minus 0.05. And we get a probability of 0.34. Well, any questions, folks, on coming up with those probabilities there? Okay, now imagine we didn't have the general addition rule. Me included, I think the most tempting thing to do in this problem is just to go this way. What's the probability Dalmatian is hearing impaired or blue-eyed? I would grab hearing impaired 0.28 plus blue-eyed 0.11. Call that my answer, but there's no way that's correct. That would never be accepted as a correct answer in my stats lab. And the reason is, really it's 0.34, because when we added those two probabilities together, there's an overlap inside there that gets double counted. That's the whole purpose of subtracting this off, so it's counted just once where they overlap. Well, we did it, folks. We found the probability. Further down in the question, it says, write down the probability statement and then calculate. Here's us calculating right here. When it says write down the probability statement, it's referring to just this part. So that is the probability statement. The rest of it, if you didn't give me probability of H plus probability of B minus probability of H and B, that would be okay. I was mainly looking for that part. So we're done with part A, but for the folks who like to think of the probabilities in a more visual way, here's method 2. So method 1 is totally analytical. What we mean by that is all we did was analyze the information, find the right formula that fits, and substituted the information into that formula. So that's the analytical approach. Method 2 is going to be more visual. So method 2, we're going to use a Venn diagram. I want to emphasize, you don't have to use a Venn diagram unless the instructions specifically say, use a Venn diagram. I don't think I would ask that on any of these questions that come up on the exam. So method 2 is only for people who, again, prefer to see it visually as opposed to analytically. Some people think best this way. Other people find that they could pull information together a little bit better if there's just some kind of picture to anchor it in. This is that picture. We start with a big rectangle. And that whole rectangle represents the sample space S. We next throw in the events that we care about. And there's really just 2 events in this situation. There is the event H. It comes out as a probability 0.28. So we write down a bubble somewhere inside the box for that event. There it is. The size of it doesn't have to be relative to the size of the probability. The whole purpose of this Venn diagram is just to organize information. We have a new event, B, but although I'm color coding, you might decide to go like this, just to label it to be specific. Even if you're color coding, it could help a little bit, I'd say. Notice I didn't put in the probability yet, and there's a very good reason for that. In the Venn diagrams, there's an overlap with H and B. The reason we know that there's an overlap is it's right there. Probability of H and B happens to be 0.05, not 0. So that means we write our event B like this. There's a bit of an overlap going inside right here. This is the event B. And this event, I need an arrow so it doesn't get too busy. That is H and B. So wherever they overlap, that's where the and gets tied in. That might feel similar to what we did with, say, the two-way tables. If we ever had an and in a problem, we went across a row, down a column, and wherever they overlapped, that was the count for the and situation. That's a big enough kind of comparison. Let's take a look at that just so we see if we can bring that in. That was chapter 3. And let's see here. Where did we do an and? I'm pretty sure we did one. Really thought we did. Hang on. Maybe it's this one. What percent of the participants have hepatitis C, but have no tattoos? Yeah, that's an and situation. We're saying hepatitis C and no tattoos whatsoever. We went down this way with hepatitis C, down this way with no tattoos, and this is the and, right where they overlapped, the 22 count. So similarly in this situation, if H and B can occur together, this is where the probability 0.05 will go, right inside the overlap. So this is our step 1. Place probability H and B in the overlap. So we throw in 0.05 right here. Does that make sense to folks so far? Okay, so that's the probability that H occurs because we're within the green bubble for H, and B occurs as well because we're within the blue bubble for B. So on the next step, subtract probably H and B from HB to get other values. So what I mean by that is, notice you cannot actually put in 0.28 right here by where the red dot is. That would be a big problem. And the problem is because anything you put in this region is the probability of H. So probability of H is 0.28. What we actually have to do is take 0.28, subtract the overlap, which is a 0.05, and put in 0.23 now. So now when you think probability of H is all of this. Let me put in some temporary shading. So it includes the overlap value, 0.05, it includes the extraneous value, 0.23 as well. And in total, all of these values at once make up the 0.28. So going in order from start to finish, you place the overlap, then you take that common value, 0.05, subtract it from here, next, subtract it from here as well to get a 0.06, and 0.06 would go into that region. Any questions at the moment, folks, to that stage? Okay, so looking at what we have, if you want to calculate the probability of B, it's not just 0.06. You're in this whole region that represents that bubble. You would take the 0.06 plus the 0.05, and that takes you back to 0.11. So we're almost done with the Venn diagram, but step 3 is use the complement rule. What we mean by that is the sum total of all probabilities is 1. So we can now go in our calculator, take 1 minus everything that we placed down, 0.23, minus 0.05, minus 0.06. And now we have a probability of 0.66. It's a complement to H or B, which means it goes outside, somewhere out here. So let's just place a 0.66 in that region, and that would do the job. Now there's a check to this. It's much the same as if you were deciding, did this model even make sense? The only way that's a legitimate probability model is if you add up all the probabilities, you get exactly 1. Same idea now in the Venn diagram, or under the curve of a normal distribution, the area is exactly 1. In a Venn diagram, just to double check, let's add these up. 0.23 plus 0.05 plus 0.06 plus 0.66. We get probabilities exactly 1. That means this Venn diagram has legitimate probabilities, and we can now start answering questions based off just that value there. It takes a minute to actually build one out, but if you find that it's just an easier way to visualize, it's not a bad few extra steps to take. Here's the benefit. Same question. What is the probability that a randomly selected Dalmatian is hearing impaired or blue-eyed? Let's temporarily highlight. Here's hearing impaired. Here's blue-eyed. Here's both hearing impaired and blue-eyed. We just take all 3 of those probabilities. Everything outside at probability 0.6, these are for Dalmatians who are neither hearing impaired nor blue-eyed whatsoever. So about 2/3 of them. We'll say here, probability of H or B is 0.23 plus 0.05 plus 0.06. Notice we didn't use the general addition rule at all. There's no subtraction here. And that's because we didn't double count the 0.05. We just wrote it in once. So we go 0.23 plus 0.05 plus 0.06. And we've got the right value of probability 0.34. So again, the Venn diagram is not required. But if it makes more sense, it's not a bad idea to use it to your advantage. I guess just a question for the class. What was your opinion so far? Do you like the analytical way or the graphic way? Which one? The analytical way? That's awesome. And probability thinking, there's a lot of value to this because there is a limit to using a Venn diagram. I just had 2 events. If it was 3 events and there's overlap on every single one of them, it suddenly becomes really, really hard to make your Venn diagram. There's actually dedicated computer software to just generate those images for you because it's so tedious. So analytically, it's kind of a fun way to go for that purpose. I think the hard thing about the analytical method is the setup and the intuition of why you even do that subtraction right there. But here's another benefit of a Venn diagram. Not every question that's asked in probability has a formula. That's another thing that's kind of awful. And part B is one of those kinds of questions. What is the probability that a randomly selected Dalmatian has exactly one of these issues? And the most important part of this was where they said exactly 1. We mean just the Dalmatians who are exclusively hearing impaired, but they have normal eye pigmentation, or the Dalmatians that have abnormal eye pigmentation, however, their hearing is totally fine. That's a whole new question, and it doesn't even line up with the general addition rule. And there's many other weird questions you can ask that have no actual rules that go along with them. Nonetheless, we can still write down the probability statement. We can say probability of H or B, but not both. So that'd be my probability statement. I had to put in ordinary words as well, just to make it totally clear. It's not your ordinary H or B. It doesn't include both at the same time. But the way to calculate this one is we come up here. The Dalmatians that are exclusively hearing impaired, what probability would you give for that? Is it 0.23, 0.05, or 0.28? For the Dalmatians that are exclusively hearing impaired, what probability would we put down? Should it be 0.23, 0.05, or 0.28?
Well, if you do 0.28, then it's both.
Exactly. That's where they're both hearing impaired and they have blue eyes at the same time. Exactly. It would just be the 0.23 on this one. That's the probability of getting exclusively a hearing impaired Dalmatian with normal eye pigmentation. So that's the first part of this one. 0.23. Let's use color coding just to show where we got it from. Plus, same issue on this one. It's not the 0.05 that's both hearing impaired and blue-eyed. It's not 0.11 because that includes those dogs that are just blue-eyed, as well as the overlap. If we want the probability of B, blue eyes with no hearing impairment, you have to pull up just the 0.06. So plus 0.06 exclusively. At no point did we have any values that included both hearing impaired and blue-eyed, because that's the probability 0.05. So if you were very careful to exclude it, that's our answer. This comes in as probability 0.29. But honestly, if you're a fan of the analytical way, you could have reasoned your way through this. When we calculate probability of H or B, or is kind of a weird word in probability theory. Or if I say something like I went to work or I stopped at the store, I think a lot of people might think either I'm at work or I'm at the store, but I didn't do both. However, in probability, or includes the possibility both occurred at the same time. So when we say probability of hearing impaired or blue-eyed, we included the overlap. But over here, if you didn't want the overlap, if you're excluding those conditions, you could have just done it this way. Take probability 0.34, subtract the overlap again, and you get probability 0.29. So the analytical way still works, but you just have to now think your way through it on how the events line up. However, for the Venn diagram on part B, it was just a matter of just grab the right stuff, add them together. So I'd say what's curious is for part A, method one is much more faster, I'd say on average. But for part B, I think the Venn diagram is not fast, but it's going to give us a more accurate answer because it's easy to represent the information and knowing what the probabilities 0.23 are talking about exclusively. But we did it, folks. Although I did put here that this is no, I did not. Good, I'm glad. I was going to say that this is probably not a fair exam question, but I didn't say that for anything on here whatsoever. So just as a reminder, for problems that make good typical exam 3 or final exam questions, let me just fix that. I'll always put an arrow on each of those problems just to indicate which ones. Well, this is the discussion on the general addition rule. Any questions at all about it so far, folks? Okay, so addition rules are tied together with or statements. But if there's an addition rule, there's got to be a multiplication rule. That's what happens in math. Probability is just applied math. And so here we go. Here is our, no, it isn't. Well, we're almost there. Our multiplication rule is down here. I guess we'll get to that one in a minute. Looks like this is going to be a question that we come back to probably on Thursday's class. So before we get to that rule, we're going to do just a quick discussion on independence versus dependence. That gets us to our first multiplication rule for independent events. And we've thought a little bit about independence and dependence, again, way back in chapter 3. So using this way back machine. In chapter 3, independence and dependence came in this kind of format. We were wondering if having hepatitis C or getting tattoos at a parlor, tattoos elsewhere, or no tattoos at all, were independent events. If they were independent, then the areas of the blue, orange, and green, I said that in weird order, should be the same in both categories. But the fact that this event, having hepatitis C or no hepatitis C, changes the areas, that told us these were dependent events altogether. We're actually thinking those same exact terms when we take a look at these ideas. So again, in a really weird way, chapter 3 was probability. But here we get to formally define what we mean exactly by independent versus dependent. It starts off by saying, two events are independent if knowing that one occurs does not change your assessment of the probability the other event has occurred. That's quite a statement. And really the best way to think about that statement is, I think most people, me included, can't really learn what independence is just by reading that. You have to attach it to some kind of an example. So that's example 7. And this is like the prototypical example of an independent event. there's randomization, and we're tossing a paired coin once again. It's going to be tossed twice, and A is going to be the event. The first coin toss results in tails. B is going to be the event that the second coin toss results in tails. Well, let's focus on the event A to start. Two things can happen if you run this random experiment. Either A occurs, or the second thing that can happen is a complement occurs. Those are the only things that can happen, because we talked about the complement. Either this happens or that happens. It creates a true dichotomy. A occurs means tails on first flip, since we're flipping coins. A complement occurs means A does not occur. We don't get a tail, we get heads. So we'll say heads on first flip. So those are our two situations. And next, let's focus on the event B. B is the event that the second coin toss results in tails. That one deserves to be color-coded. We're going to calculate the event B twice. This might look a little bit weird, but just use your intuition. In the case A occurs, you flipped your first coin and got tails on your first flip. You go to flip it again. What's the probability of getting tails the second time? Exactly, it hasn't changed, right? It still should be 50% or 0.50 or 1/2. Same thing we said at the very top of these notes last week. And this is actually kind of tied into something called a gambler's fallacy. Imagine that you were watching, say, coin flips. Maybe you're, I don't know, gambling or something. And then you notice that tails got flipped 3 times in a row. You might decide, I'm going to bet on heads on the next flip. There should be a higher probability of that occurring. But actually, that's false. The probability of heads, even if tails came up 50 times in a row, which would be spectacular, maybe it's not even a fair coin, but if it is, probability of heads on the next coin flip is still 50%. There is no influence here. Likewise over here, imagine you flip a coin once and you got heads. What's the probability of tails when you pick up that coin and flip it again? Exactly, no change. So it equals 0.50. And so that's what we mean by independence. We looked at two situations. A occurs here, or does not occur over here. But either way, probability of B is exactly the same. Reading the definition, two events are independent if knowing one of the events has occurred does not change your assessment of the probability of the other occurrence. That's the probability of the other occurrence, still 50%, no matter what happens to probability of A. So here's our conclusion. This shows A, B are independent since the probability of B is not influenced by A occurring. So that's our prototypical example, once again, of events that are independent. Oftentimes randomization gives lots of independence. So in our next problem, it says something about randomly selecting 4 25 to 29-year-olds. That alone is telling us there is independence in this problem. We'll come back to that when we go to solve that one. So that's the definition of independent events. But we also need a definition of dependent events. Some textbooks literally do this. They say a dependent event is an event that's not independent, and then they just stop. I think that's kind of rude. Dependent event is interesting in its own right. They should really just flesh it out. And so that's what we have here. Two events are dependent if knowing that one event has occurred changes your assessment of the probability that the other event occurs. So there's a lot of examples of dependent events, but I want to be a little bit more creative since example 7 is possibly something you read right out of a book or a different book for independent events. This one is all our own. I've been watching carefully that no one is ever named Joel in our class so that we don't have Joel coming up as a real student. And I want to add just one additional phrasing here, just to make the problem seem more logical. Let's say that Joel only drives if he is going to work. Let me highlight that part in red for the edit. So here's the situation. It says when Joel drives to work, he parks illegally. So this is just what Joel does. Maybe he doesn't want to talk to people, get a parking pass. I understand that. We also know, because we put it in the edit, Joel only drives if he's going to work. Next, it goes on to say, when Joel parks illegally, here he's at work, there is a 6% chance he gets a parking ticket. He's just going to run with that and hope for the odds. But we wonder next, are the events of going to work and getting a parking ticket independent or dependent? And we have to explain. Well, it's probably dependent because we know we're doing that example next. But just on the write-up, anyone see what element makes it dependent?
He's only capable of getting a ticket if he goes to work.
Exactly. So that's the big change on this one. That's going to influence the probability of getting a parking ticket totally. So let's break it down just like we did before. There's two events. There's getting a parking ticket and there's driving to work. So let's code those up. D, that's going to be the event. Joel drives to work. And let's let, I guess, T makes sense. T is the event that Joel gets a ticket. So now, breaking it down the same way we did on example 7, let's focus on the event D. Two things can happen. Either D occurs.
Sorry, you said D was the event. What did you say T was?
The event that we get it, Joel gets a ticket.
Liberal events.
Exactly, yeah. So in one case, either the event D occurs, that means Joel is driven to work, he's getting paid today, or D complement occurs. That means Joel is not going to work. Maybe it's a weekend, maybe he's sick, maybe the car broke down, something along those lines. All we know is if D is the event that Joel drives to work, D complement written this way means Joel does not drive to work. Let's actually say that below, since we're getting used to that symbol as well. Joel does not drive to work. On this one, Joel drives to work. So now that we've done that, the next event that we're going to focus on is getting a parking ticket. So we call that the event T. Might as well color code that if we're color coding it there. And we want to calculate probability of T in both situations. Well, this one's not so bad because it straight out told us there's a 6% chance that he gets a parking ticket when he parks illegally. We also know he only parks illegally, but that's when he drives to work. That's the only time Joel drives. So if the event D occurs, he went to work, he's parking illegally, and there's a 6% chance of that ticket. But what about over here? Anyone see what the probability should be for a ticket when Joel does not drive to work? Exactly, and that's with the edit right here in red. We're assuming he only ever drives to work, so he's not getting any parking tickets for sure if he didn't go to work. This happens at probability 0. You could call it the 0. That means it's an event that cannot happen. There's no possibility of a ticket this time. But also look what happened to our probabilities. The probability of getting a ticket, T, depends entirely on the event D, it occurring or not occurring. Probability changes this time. So these events are not independent, like above. Probability was stabilized. These are dependent events. We'll say here, the events D, comma, T are dependent since probability of T getting that ticket depends on the event. D, occurring. Or not. So that's what a dependent event could look like. Again, there's a lot of dependent events out there, but that's a more different kind of one for a more realistic real world situation, I guess you could say. Well, any questions at all, folks? Thinking about independent events versus dependent events?
So is it always gonna be dependent if the event D occurs is 0?
There could be other ones. This could have been in a different situation, maybe probability 0.07 or 0.08. Just if it changes at all, that's going to be dependent. Other questions at the moment? Okay, well, this takes us and segues us to the multiplication rule. But this multiplication rule has one massive disadvantage. It only works if you have actual true independent events. Essentially, there's some parallelism here. We did an addition rule that only worked if your events were disjoint. That's this rule for multiplication. Then we segue to a rule that's general, that you could use an addition rule in any situation. And that's what we'll be doing on these notes. We'll look at the general multiplication rule, and that will be our last question. So these last questions that we're doing are more just to help us out thinking about independence and dependence, to support the MyStats Lab homework. But I think we're getting to the examples where these won't be very good exam questions at this point. So these are more to support the homework more than anything else. But any last questions then, folks, before we call it a night? Okay, well, when we come back, we'll be finishing off these notes, going into chapter 13, and I hope to have an answer if the course coordinator, Christine, she's a nice person, has any inclination on what to do if you click on this button when you've opted out. It's going to convert to something that says, give it a minute, says buy now. So if it says that, it means you opted out of the courseware. And if that's not true, let me know. It means there's just a mistake somewhere. Say again?
Mine had the other book cover on it.
Very strange. Yeah, it should look just like this with the buy now.
My computer had the MyStats Lab book on it when I clicked on it.
Very strange.
Oh? No, I'm sure.
Well, I'll look into that with the course coordinator and try to get those things figured out. Hopefully we'll have an answer Thursday, but in case she's a little bit slow, busy week maybe, I'll definitely have an answer sometime on Friday on what the next step should be.
Did have the cover of the book.
You know, there's a good chance people are fixing things as we talk to try to make it work. People are discovering these problems as they happen. So there might be already people working on this. Who knows? That's me being optimistic. But any other questions at the moment?
Exactly.
Okay, well, have a great night, folks, and we'll get back to this next class. I think you said chapter 7 stuff.
Yeah.
Cool. So how's it going so far in there?
Three or four. We're actually up to 2.
So I got question 1, but 2 and 3,
All the other you got no work?
I can't get past like question B and there's like a tie.
Yeah, that's rough. Sorry about that. That's why it's only 3 questions on this one.
I'm sure he saw it.
So what does this B naught value mean in the context? So B naught is the intercept, and you've got intercept at 0.865. Now, what was the context? Manager of a bookstore wants to predict sales from the number of salespeople working in the accompanying data. So number of salespeople working is the x-axis. Sales is the y-axis.
Right.
So that'd be a y-intercept for value in sales. Let's see.
So how do you get that?
Oh, so did you put it your data there into your calculator?
Yes.
And in your calculator, you go to the stat button, go to the calculate tab, and then down to option 8.
Okay. And that's it?
Yeah, so it pretty much looks about like this over here on this calculator. I think I should have some data in there. Go stat, let me just check the data. Oh, I need to have stuff over here on the right as well. Let me just delete some stuff and then some random data. See you later.
Thank you.
Okay, that should do it. So hit the stat key and it looks like that.
Mm.
Go over to calculate. Down option 8. Gives you all this stuff, but the A value right there, that's what they're referring to in their book as B naught, the intercept.
Oh, okay. So then how do you find this one?
Find
Without
the
that.
slope B1. The B1
Yeah.
is gonna be the value right below it. So that's your B1 value and that's your B naught value.
Oh, okay. Oh, that makes it a lot easier. then.
Cool. I think it's awful because the calculator says it one way and then our book says it a different way.
Okay.
That's just awful. Sorry about that.
That makes more sense. Thank you.
Yep, absolutely.